the normal force, not the weight. So we have a normal force going in this direction, and that's my angle theta. I know one of those will be cosine of theta, y cosine theta, the other will be y sine theta. It's a question of which one. Well, if this angle here is theta, what is this angle?
That's also theta.
And therefore, what is this angle?
That's not theta.
Okay, so if that's not theta, then that's gotta be theta.
Mm-hmm.
So the horizontal piece is the sine, so this becomes y sine theta. And this is y cosine theta.
How exactly are we gonna break that up? Like, that way that?
Yeah, the horizontal is y sine theta, the vertical is y cosine theta.
Okay.
Is it always gonna be like that? Like, when box on ramp, the side going down is always sine theta?
It depends on what you mean by always. So yeah, given the angle with respect to the horizontal here, y would break up with sine and cosine. If you're going with always, that the sine is always in the direction of acceleration, no.
Okay.
So we end up with, so what I'm claiming then is that this force diagram can also be written as y cosine theta, y sine theta. Wait. When you are breaking it up into components, try not to put the components on the same diagram as the other vector here. I know what people are doing, but if you put y sine, y cosine theta, and y all in the same one, it looks like you've got two different normal forces involved. That's just, it's bad form. All right, so we decomposed. Now what?
Equations of motion.
How many will we have?
Three.
What three?
Three. No, it's actually just two. Because there's only two coordinates
And one object.
in one object.
All right, so what are the two?
It would be y cosine theta, or j hat. It's the j hat.
Okay, so the j hat equation.
Y cosine theta. Minus w equals ma.
We can do better than that.
Zero.
Yeah. If done correctly, and the problem's, a standard one, just picking one of the equations, the acceleration should be zero. Unless again, you're just a masochist, or just enjoy the math. All right, so if the j hat's been done, that leaves I hat. Okay.
Then we get onto this S, first S. Substitution on S. The W becomes mg. So y cosine theta minus mg, or equals mg.
Whichever way.
And then y.
I'm done. I'm writing it down here for a reason. Equals mg. All right, and the other one.
The other one stays the same. Now.
Oh, whoa, we have another substitution.
Oh. What was it? V squared over R.
And using the v squared over r instead of the omega squared r is probably the choice we want to take because we're trying to find speed. That's that word right there. So if the road is frictionless, at what speed should the car go so that it does not slide up or down the bank?
Upward.
So we're finding that nice ideal speed.
When we say bank, we're talking about like,
A road that's tilted,
Like a racetrack.
like a racetrack.
when it's tilted in the curve.
It's tilted so that you can, so on a flat road, you can just go straight, no problem with that. But if you're going around a curve, if the road is flat, then you're relying upon the friction between the road and your tires, so that you bank it some so that normal force helps.
Okay. You're a celebrity today, Dr. Fox.
All right, pardon?
I said you're a celebrity today. Your phone's blowing up.
You know, when you're a physics instructor, you can't help but just deal with the fame that comes. All right, so we have two unknowns here. I don't know V. Oh, I didn't tell you R, so let's give you R. And you don't know R.
Or is just the radius like normal?
Radius of curvature, right?
Curvature.
So if I'm dealing with a curve that's going like that, so it's not actually a circle, and the car is at this point, the radius of curvature is to pretend this is part of a circle.
Yep.
And the radius of curvature is the radius of that circle at that point.
And all around that curve would it just be 100 constantly?
If it's truly a circle, yes.
And if the curve was... Okay.
Okay.
So at all points throughout that wavy line, or
No, I'm saying, if it's a perfect circle, then I've got one radius and done. If I've got a wavy line like that, then it varies. So I have a radius of whatever that is, it will change, my radius will be 0, my radius will be infinite, and then my radius, then the circle flips from this side to that side.
radius is infinite.
Yeah, on a flat curve,
Okay, got it.
so it's flat at, somewhere between that and that, it's considered flat.
And then it flips.
Yeah. All right, so how do we solve this? Besides magic.
Well, part of me was thinking like something with tangent.
Yeah, that probably would be convenient. So I'm just gonna suggest, some people, you got two unknowns here, we got Y and we have V, so those are my unknowns. In this particular case, since I know M, G, and theta, I could solve for Y and then plug into there. Boring. Because this type of maneuver shows up enough times, I think it's convenient. I'm just gonna divide the left sides and divide the right sides. So now I get tangent of theta, the y's cancel out. And over here, the masses cancel out. And I'm left with v squared divided by gr.
So you just... What did you divide the y sine theta by? And then
All right, so the math people tell me as long as I divide both sides by the same thing,
Mhm.
not 0, I'm good. Well, I divide the left-hand side by y cosine theta,
Okay.
and I divide the right-hand side by what it's equal to, mg.
Oh, okay, that works.
So...
The denominators are equal, you figured that out here.
Mhm.
Awesome sauce. So,
And so therefore, v is the square root of gr tan theta.
how'd you get that? Was that like that transition between that and that?
Okay, so I'm solving for v,
Right,
so I have to get rid of the stuff that, the hanger on.
okay.
So I got this gr I need to get rid of.
Okay, so you multiply it to the other side, then you do the square root.
Yeah, multiply both sides by gr, and then, as you said, square root.
Yeah.
And now, in all the excitement, notice that the mass of the object does not matter here. The speed is equal to the square root of 9.8, so it takes place in Earth 1, times 100, times the tangent of 25 degrees. And we end up with a magic speed of 32.7. It's gonna be less than that, say 22.7. In some unit system. Actually, if I'm gonna ignore units, the answer is 1.
31.377. Not 31, 21, sorry. I think, yeah.
Units?
Meters per second.
Now, if there is friction, which way is friction gonna go?
No.
I think it's going to go up the ramp, because when you're on a slope, you, like, let's say the slope is ice, you slide this way, so friction would be opposing that.
That is true, but why, but we're driving. We're not just sitting there, we're not parked. If we were parked, yes, absolutely.
So, it'd be backwards. Because if you're going forward,
Yeah, this does come into the fact that there are, if we're throwing friction into it, then we actually have 2 frictions involved here. We have the friction of wheel on tire because the wheel is spinning one way, and then we have the friction that deals with whether the car's gonna slide up or down the ramp. So we're concerned with up and down the ramp here.
Oh.
You're saying down the ramp, you had speculated earlier, up the ramp. And the answer is,
Neither.
it depends. Condition. We found the ideal speed. At that speed, doesn't matter if there's friction or not, the thing's just gonna go around. There's no friction, friction's not trying to keep it from sliding up or down the ramp. If I drive slower than this on that banked curve, which way am I gonna go? Which way will I slide up or down if I drive slower than that?
down,
You'll slide down.
In which case, the friction would act
up the ramp.
up. If I'm driving faster than this, which way does my car want to slide?
Up the ramp.
In which case, the friction is acting,
Down.
yes. So, just be careful of that, sort of think through the process. So then we can also, so we got some variations on this, and I know we gotta go, some variations on this of, I can throw in friction, what's the maximum speed now? What is the minimum speed? Or, he's driving 30 meters per second, what is the minimum coefficient of friction to keep it from sliding up that ramp? Just, a lot of neat junk like that, but alas,
That's the
we would need to perfect the time machine and finish it.
I just clicked that that's the back of the car.
Yes. And it's square because I did a sign on
Yes.
XB.
That makes so much more sense.
Okay.
I was like, wait a minute. But, okay. Yes.
Welcome to the class.
Welcome to the club. I was all there, but then sit there.
All right. Also on the last parting note,